The purpose of this lab is to help you understand the characteristic of ellipses and relate it to Kepler's third law of motion. Now, here is a diagram of an ellipse. Points marked 1, 2, 3 are positions of a planet at different times in its orbit around the Sun. For each point in the orbit, draw a straight line to each focus. For example, join 3 to F1, join 2 to F1, and join 1 to F1. Similarly, join 1 to F2, 2 to F2, 3 to F2, and so on. Now, record those distances. Measure and record distance of point 1 from F1, point 2 from F1, and so on, and do it for F2 as well. And then add those two distances. Now, which two distances are added? One measures distance from F1 and its distance from F2. Add those two distances. For point 2, distance to F1, distance to F2, add those two distances. Similarly, do it for all 3 points. Now, answer these questions. In other words, the question 1 is, what do you notice about the values in the last column? Make a statement about it. In exercise 2, draw a straight line through the widest part of the ellipse. In other words, draw a straight line, say from here, going through F1, F2, and cutting the ellipse here. Now, measure that distance and compare it with the distances you measured. In other words, the sum of the two distances you did in activity 1. The length of this line is called the major axis. That line is the major axis. Now, very often we deal with a distance called the semi-major axis. Semi-major axis is 1/2 of the length of the major axis. So record and measure 2A, where we used A for the semi-major axis and 2A for the major axis. So record the length of 2A and then the length of A. Let me now explain activity 3. The path of a planet around the Sun is an ellipse. The Sun is located at one of the focal points of the ellipse. Now here we have an ellipse with 2 focal points, F1 and F2. I want you to join the 2 focal points so that that line cuts the ellipse, say at points B and D. All right. Now mark the center of that line. That is the center of that line, and label it as C. This point is called the center of the ellipse. The distance BD is the major axis, and the distance BC is half of the major axis, and we call it the semi-major axis, and we represent it as lowercase a. Now I want you to draw a line at right angles at C so that it will cut the ellipse at A. Now remember, you need to use a ruler to draw these lines. I'm using my mouse and with my left hand, and it doesn't come as straight lines. Now measure the distance AC. What do you think that distance is? The whole length of this axis is the minor axis, and therefore AC is half of the minor axis. We call it the semi-minor axis, and we denote it by the letter B. Now join the point F1 to A and measure that distance. Now, what do you think that F1A will be equal to? That F1A is actually equal to A. Now, what are the measurements therefore you record? Measure distance BC and record it as A. Measure distance AC and record it as B. And measure distance F1A and record it as lowercase a, semi-major axis. Now, the distance from the center to the focus is called the focal length. So, F1C is the focal length, and F2C is also the focal length. We represent the focal length by the letter lowercase f. So measure distance F1C and label it as f. So how many distances do you have now? You have measured A, you have measured B, you have measured F1A, which is the same as A, and you have measured the focal length f. Now, what I want you to show is plus f squared. Use your measurements to show that this is true. Now, if this is true, what can you say about the triangle F1AC? An important characteristic of an ellipse is its eccentricity, which we denote by the letter E. And what is E equal to? E equal to the focal length f divided by the semi-major axis. F over A is called the eccentricity of the ellipse. And what does it indicate? Now, what is the eccentricity all about? If a diagram is a perfect circle, its eccentricity is actually 0. As the circle gets flatter and flatter, its eccentricity increases. In other words, the characteristic of an ellipse given by its eccentricity actually determines what type of ellipse it is. If you study the motion of planets around the sun, by studying the eccentricity of their elliptical paths, we can determine whether the path belongs to planet A or planet B. Or that the focal point F, or let's call it F1. That's what we've been using. So that's the focal point. Now what you need to do, now remember, before you start work on this, you need to print out this page or any page that you want to work on and do exactly what I'm illustrating on the printed copy. All right. Now draw a vertical line passing through F1. Now you got to draw an exact vertical line. I'm using my mouse so it doesn't look, it's very crooked. Now you got to use a ruler and do an exact vertical line. Now mark the center of that line. That will be somewhere here. All right, and that's called C. And what is the distance C F1 called? What is the distance of the focal point from the center? That is the focal length, lowercase f. And what is this distance called? From the center of the ellipse to the extreme end. That is the semi-major axis A. So you have the lowercase f, the focal length. Now remember that in this case that f will be a very small number compared to A. Now calculate the eccentricity of the ellipse E equal to, what's the formula for eccentricity? E equal to f over A, and use this value of eccentricity. Go to the table that I've gave you and use this value of eccentricity and see if you can identify planet A. All right, and do the same thing for planet B. Okay.